Hello, I'm Mateusz Kobak. I work at Phoenix Systems, and together with Agnieszka Frąc from Atende Industries, we'll give a short presentation about the energy use case. So, what is the main concept of the energy use case? Well, we are seeing the ongoing transformation in the energy sector in terms of the energy production from the centralized system into a more distributed model. And one of the challenges that appear here is the managing of distributed devices that not only consume but also produce energy. And we claim that electrical energy meters could be used to tackle this challenge on the level of a single household. Our main goal is to maximize the usage of local green energy, and to achieve that, we use smart energy meters powered up by AI decision algorithms. On the one hand, thanks to the Phoenix RTOS operating system, smart energy meters can run many complicated applications, but on the other hand, they still remain limited by the resources of the platform. The COGNIT framework provides a simple way of enhancing these capabilities of smart energy meters with external computational resources. The computationally intensive tasks are offloaded outside of the device. Here, we can see a simplified reference scenario, which is well pictured on the diagram. There's a couple of households with a varying set of appliances that are to be controlled by the AI model. There is the Bismart Energy, which is a platform for storing and managing energy-related data. And there's the COGNIT framework, together with the serverless runtimes, where the AI functions are offloaded. The most important actions that are periodically done by the meter are listed here below and are the following. So sending meteorological data to Bismart Energy Platform, offloading of the AI model inference and applying the results to the household appliances, and offloading the evaluation function of the AI model, and also model retraining if necessary. And now Agnieszka will take over and tell us something about the decision algorithm.
Okay, thank you. Now let's focus on the decision algorithm for our use case. The slide illustrates the concept of a home energy management system and how its components communicate. In a typical home setup, we can identify several types of devices: energy sources like photovoltaic panels and external grid, appliances consuming energy, both uncontrollable ones that are always unactivated by user demand, and controllable devices that this can adjust energy usage, such as heating, ventilation, air conditioning system, and electric vehicles. Battery energy storage system can be charged to store energy and discharged for later usage. The smart energy meter monitors these devices, collecting real-time data on their operation, including energy exchange with the grid and PV production. This data is sent to Bismart Energy platform, while the smart meter can adjust device settings. It lacks the computational power to make optimal decisions using AI models. That's where Cognit infrastructure comes in, executing the decision-making algorithm, what is represented in the scheme by a reinforcement learning agent. The algorithm consists of three types of functions. Training function, whose task is to create a model ready to make energy-optimized decisions using a longer period of historical data from Bismart Energy. It's computationally intensive and is offloaded on demand or based on evaluation results. Evaluation function assesses the model effectiveness by simulating its performance over a given period of time, using simulators of end devices in the household. This function evaluates whether the model needs retraining based on specific metrics. It is offloaded periodically based on a user-defined frequency. The last one is decision-making function that uses the trained model to make energy management decisions for the next time step, optimizing device settings for the day. Its execution is quick, and offloading takes place periodically with a user-defined frequency or on demand. After doing literature review and researching various approaches, we decided to develop a home energy management system algorithm with usage of reinforcement learning, specifically proximal policy optimization method. In PPO, agent consists of two models, the actor and the critic. Input for both models include time of day, predictions of PV production and uncontrolled energy consumption, indoor and outdoor temperatures, state of charge of energy storage battery, and EV status, that is, time till its departure, availability, and battery state of charge. The actor's output defines three actions: temperature setting, storage charging or discharging power, and EV battery charging power. These actions are then executed, changing the environment state, with the critic evaluate by predicting the reward. The total reward is based on self-consumption, temperature comfort, violation of battery energy levels, and for EV, both violation of battery energy levels and readiness of its departure. The iterative process continues until the agent converges and finds a policy that maximizes the expected cumulative reward over time. Now that we gave you an overview of our use case and its algorithm, we will demonstrate a running example. We'll showcase two environments, a fully simulated one using Python version and a laboratory environment with real smart energy meters offloading functions using a device runtime client in C. Thank you. Let's start with the Python demo. I'm going to run an example with a single smart meter simulator in the window in the upper left corner. In the upper right terminal, we can follow logs from the household simulation and all end devices defined for it. This demo runs with a speedup of 300, meaning every virtual 5 minutes lasts 1 second. As we can see, device statuses and related energy consumption change over time. Since there is no energy production at night and the battery storage is empty, the load must be supplied from the external grid. In the bottom left corner, we have logs showing the status of function execution within the COGNIT infrastructure. The decision-making function is offloaded every virtual hour. 3 runs have already been completed and returned results. More details about these functions, especially input and output parameters, are available in the user app file displayed in the lower right window. Based on these decisions, settings for the heating controller, storage, and EV batteries are updated for the next hourly step. Every 4 virtual hours, the evaluation function is also floated. As we can see, the required metric level wasn't met, so a new model must be trained for this household. Training takes a few minutes, so I will skip ahead. Here we can see the output indicated that the training took almost 6 minutes and the model was saved successfully. Immediately afterward, the next decision-making function was triggered to update appliance parameters using the new model. The Python demo can also simulate many devices running simultaneously, so I would like to show an example with 20 meters. The process is running, and as before, we can follow simulation activity and offloaded functions. Households have different offloading patterns depending on user preferences, but still the requests may overlap, resulting in many offloads at once. As shown, all of them completed successfully, which means COGNIT scaled correctly and provided enough VM instances with the required resources. We can inspect logs for any household, so let's switch the file displayed in the terminal in the right upper corner. As expected, they look similar. Statuses, parameters, and metrics evolve, and virtual time advances at the same rate. In this example, we have 2 electric vehicles, which are handled individually, so decisions are made for both. Let me also open the log that tracks offloading for this household. Training is currently in progress, so we need to check all the logs for more context. We can see that the previous evaluation failed, which is why training was triggered. Those error logs show the model's selected settings for all end devices, including the two EVs. That's everything I wanted to cover in such a short time, so I will now hand the floor back to Mateusz.
Hello. This is our demo setup consisting of 4 actual smart energy meters. Each meter is running our COGNIT use case demo application alongside the meteorological facility and is based on the Phoenix RTOS operating system. The Raspberry Pi here in the middle is running the household environment simulations for all of the 4 meters. Each meter is equipped with a GSM modem, which is right here, which provides the internet connection which is necessary for the usage of the COGNIT framework and for offloading functions. Moreover, each meter talks to the Raspberry Pi via the RS485 interface, which is right here, in order to obtain the state of the household devices and to set their configurations based on the result of the decision function. Now I will show you how this demo works in practice. You can see 4 panes and each of them plays a role here. In the upper left corner, I am connected to the console of the smart energy meter via the optoelectronic link, and we can already see the logs from the COGNIT demo application. Evaluation, training, and decision function have already been offloaded. In the upper right corner, I'm running the household simulation process in an interactive Python session. And for that, in the bottom right, we can see the live state of this household simulation and how the parameters change dynamically. And finally, in the bottom left, these are the logs from the edge cluster that we have here in Warsaw in our office. And now I will manually trigger offloading of the decision function. We can see that the decision has been offloaded from the meter and that the edge cluster has received the request and the decision function has been successfully offloaded. The result has been received and they have been applied to the configuration of the devices. That's all from me. Thank you.